Newton's third law of motion is one of the most memorized but also most misunderstood statements in all of science. Simply stated, the third law of motion reads, "For every action there is an equal and opposite reaction." A very short sentence and easy to memorize. However, a better way of stating this might be to state it a little bit longer. Whenever one object puts a force on a second object, the second object puts a force back on the first object that's equal in magnitude or strength, but in the opposite direction. Instead of calling the third law of motion the law of action and reaction, it might better be stated as the law of interaction. A force cannot be exerted on an object without that other object exerting a force back on the object that exerted the force on it. If I take two spring scales and hook them together, whatever force I pull on one will be equal to the force on the other. These two scales will read the same value as long as there's no friction or anything else impeding them. When the scale in my right hand puts a force on the scale in the left hand, the scale in my left hand puts a force back on the scale on the right that's equal in magnitude but opposite in direction. So at this time they're both reading about 16 newtons, 6 newtons. So if you tried to pull with one scale, say with 10 newtons, and the other with 5, it would be impossible, because the only way this scale in my right hand can pull with 10 newtons is if the scale in my left hand pulls back with 10 newtons. This also holds true if we connect the two scales to strings. The scales don't have to touch each other. Again, whatever I pull with one, the other pulls back with the same amount. Another practical application of Newton's third law of motion is in collisions. When your car is rolling or driving down the road and you hit a bug on your windshield, the car exerts a force on the bug, and the bug exerts a force back on the car. It might seem like the car puts more force on the bug than the bug puts on the car, but they put equal and opposite forces. The force of the car on the bug is equal to the force of the bug on the car. Now the forces are equal, but the results of those forces don't have to be equal. The force that the car puts on the bug does a lot of damage to the bug, but that small amount of force that the bug puts back on the car does very little to the car. However, if the bug was bigger, say like a deer, the force of the car on the deer and the deer on the car would be equal, but that would be a large enough force to probably do some damage to the car. Newton's third law of motion is always true, regardless of the situation. Even when you think the forces aren't going to be equal, they're going to be equal. I've got the red dune buggy and the blue dune buggy. Suppose the red car is moving along and hits the blue car while it's parked. Which force is bigger, the force of the red car on the blue or the blue on the red? A lot of people might think, oh, the force of the red car on the blue has to be bigger because the blue car wasn't moving. However, Newton's third law says it doesn't matter if you're moving or not. If one object puts a force on a second object, the second object puts a force back on the first object that's equal in magnitude but in the opposite direction. So when the red dune buggy puts a force to the right on the blue dune buggy puts an equal amount of force on the red that's to the left. That force that's on the red dune buggy stops it, or at least slows it down. What if they're both moving toward each other? What if they're moving toward each other with equal speeds? How does the force of the red on the blue compare to the blue on the red? Well, in this case, they have equal masses, they have equal speeds, so most people would say, oh, those forces are equal this time. But they would say, but if the red car was going a lot faster than the blue car when they collided, then the force of the red on the blue would have to be bigger than the force of the blue on the red. That's not true. Newton's third law says it doesn't matter what their speeds are. If one puts a force on the other puts an equal amount of force back on the first. So this is true if they have the same mass and one's moving and one's not, or if they're both moving at the same speed, or if they're both moving at different speeds. This is even true if they hit from behind. Red dune buggy's going 30 miles an hour, the blue's going 20, catches up, hits it from behind. The force of the red on the blue is equal to the force of the blue on the red. The force of the blue dune buggy on the red slows down the red dune buggy. Now, these are cases where these cars have equal masses, but what if they don't? What if the little red hits the big green car? Now people would say, oh boy, the big one's got to put more force on the smaller one. No, Newton's third law of motion says no matter what's going on, hitting a stationary or both moving, catching up and hitting from behind, regardless of which one is in the front or which one is behind, or how fast they're going, or how much mass they have, when one object puts a force on the other, the second puts a force back on the first, that's equally strong but in the opposite direction. Newton's third law of motion is always true. It's impossible to come up with a trick question where the two forces would not be equal. They will always be equal. The one thing you have to be careful about is looking at, are these forces actually third law pairs? It's a third law pair if A acts on B, B acts on A. Two objects, two forces. Those are always equal. But in a case where object A puts a force on object B and object C puts a force on object B, those don't have to be equal. They're not third law pairs. If you've got three objects, then it's not a third law pair. Third law pairs, A on B, B on A, always equal. But A on B and C on B might be equal, might not be equal. That's where you have to be careful. Identify the objects and the forces in question. Third law pairs are always equal. Other pairs of forces don't have to be